So we'll see.
Hey, Mr. V,
Yes, sir.
you still want me to show that video on glove testing?
Would you like to take care of that today?
Yeah, I can do that.
Hey, I'm all for it. Go ahead, Lenny.
All right, guys, I found a video on glove testing. Just ignore the Canadian accent, okay? Don't get the...
Take off, eh?
All right.
Well, don't mute yourself, then we can't hear you.
Sure. You guys see my screen?
Yes,
Yep.
sir.
Awesome. Sorry.
We started hearing some audio, then it went away.
Still can't hear me.
No audio.
No audio. No audio.
No audio still. Can you hear us, De Los Santos? De Los
Hey,
Santos cannot hear us.
Lenny.
We could watch from the words. Trap the air in the glove, pop fingers out and visually inspect the surface. Look in between the fingers. And turn it the other direction. Inflate it. And repress it. Look for nicks, cuts, cracks, or holes. That's a good thing to look for.
Yep.
You want to look for damage of any type. Then he's got this cool little gadget called the Salisbury glove inflator, which I never used. One thing to be especially aware of here is don't overinflate the glove. Just enough to get it just a little bit over regular size of your normal hand. And listen for leaks and feel for air leaks coming out. Don't let the glove fly off and hit you in the face. Oh, there's Al. In that neat little nifty case. So we'll talk about that, sending it to a lab. And thanks for watching.
Hey guys, so I mean, I've seen multiple methods. I mean, you could do it with you don't have to use that inflator. You can do it with your mouth. I mean, blow in your gloves. Yeah, go ahead, sir, Mr. V. You got this.
Go ahead.
Yeah. I mean, I've seen people, either roll their glove like he did to see if there's any air come out. I've seen people put water on the glove and apply pressure to see if there's any leaks coming out. And also I've seen people just blow on the glove, so, but go ahead. I'm gonna let Mr. V take the stand on this. So.
Okay, cool. You can go ahead and unshare there, Lennon. All right, go ahead, Mr. V. He wants you to take the, not me.
Well, I've got just so happen to have one of these handy dandy glove testers. in my hands as we speak, just what he used. It is a good tool to use for checking your rubber gloves, but there's really, in my opinion, guys, when you're checking your rubber gloves, this is an old glove that Professor Shoemaker had. We've got a couple of different pairs in the trailer out there on the yard if you guys want to look at them, but there's nothing like putting them in your hand, rolling them up, doing an air test yourself by rolling the ends of it up like this, inflating it. Of course, this is an old glove. It's not to hold air. It's got holes in it, but you want to take and put it to your ear and listen and feel for air leak in these gloves. If you do come upon an air leak in the glove, you want to destroy the glove. However you need to. Cut the fingers out is the best way we've always determined. That's always your best option, to cut a finger out, throw it in the trash. That way nobody can use it to do any kind of hot work. Very important step to do. You want to test your gloves. We used to test them just daily when I first started with the power company, and then we moved to checking them before every time we did any kind of hot work. Very important to keep them stored in a clean, dry place on your truck inside the bag that it comes in. You saw in the video, it had a rubber glove bag, and always said, keep your gloves stored in the bag in a good, dry place. You just want to make sure that you have these out of the way. You just don't wear them for work gloves, because these are your lifeline. And this is what I like to call, this is your PPE. So it is your personal protective equipment. That's your personal protective equipment. Everybody should receive their own pair of gloves. It's going to be up to you to make sure you keep up with your gloves, to make sure you test your gloves, to make sure you keep them safe and clean, because they are your lifeline. It's okay to let somebody borrow them if they need them right then, but it's your responsibility to keep these gloves, free of holes and cuts and those kinds of things. So, Professor Shoemaker?
The most important piece of personal protective equipment you'll ever have.
Yep.
He brought up all the major points that are going on right there, and I'll just reiterate. It's sometimes you'll see, well, I found a hole in my glove, or I found a defect in my glove, and then you'll just take that glove and throw it on the back of the truck, and then somebody will see them and pick them up and say, these look pretty good, I'm going to use them. Some guys will even say, well, they're not good for the voltage they were rated at, but I can use these at the house for 120, 240. No. Take and cut the fingers out so nobody can use them at all, ever. He did bring up also, Professor Reed brought up also putting them in a regular storage space. We had a specific bin for all rubber goods, including rubber gloves, and that bin's got to be free of all petroleum products. So you can't put chainsaws or fuel or cable cleaner or anything like that in that bin, because that'll deteriorate a rubber glove. A rubber glove is not to be left out in the sun. So keep them in the bag as much as possible unless you're using them. And Professor V, could you do me a favor?
Yeah.
Roll that glove up again for the test. This is the most common one.
This is what you do. You roll it.
Roll it until it inflates. Now, guys, after you roll it and check it from there, what's not tested?
The bottom of the glove.
Right. So from about here down, the cuff is not tested. You test.
Shoemaker,
Yes, sir.
why are you trying to get in?
Somebody's trying to get in.
Yeah.
Call the police.
I guess you the sheriff of the town right now to let him in the Zoom. You say you're trying to get in.
Who?
Who is?
Khalil.
Well, they ain't trying to get in here. There's no.
Khalil's right there.
Khalil's right here. What?
Yeah, he's kicked back on the couch.
Yeah, like he's
No, it's Jordan.
Jordan.
Jordan,
Yeah, he said he's trying to get in.
There's no notification for us that he's trying to get in. Okay, anyway, the cuff of the glove is not tested.
Yep.
All right, just there he is.
Hey, Jordan.
Okay, just probably from about the wrist up is tested in that test. Now, Lennon, you did bring up, some people put water in them. Some people blow in them. I mean, I've seen the water test. I've not seen anyone blow into a glove to try to inflate it, but the wrap test is most common.
Yeah.
And we'll emphasize again, how frequently do you test your rubber gloves?
Before every use.
Every use, before every use.
Daily.
Yep. You don't know who's used them. You don't know what's happened in transit. Somebody might have dropped something on them that was sharp.
Yep.
You do not handle any steel cables with it, like pulling cables and whatnot. Obviously, you're going to be working with conductors as far as power lines are concerned, but steel pulling winch cables and winch cables that come off a boom that are steel, you do not use those because they puncture real easy. And Professor V, what was your schedule as far as setting them off and getting them back?
Started out before we were Duke, we sent them, really, we changed them out once a month, but then Duke, it was like every 3 months.
Okay. Depending on your company policy, ours was once a month. Your gloves are going to be, you're actually going to have one set of rubber gloves that are off in testing in a testing lab, and you're going to have one set of rubber gloves that's on your truck that goes with you all the time. Now, Santee Cooper, we talked about this before, they have a distribution voltage of both 7,200 phase to ground and 19,900 phase to ground. So they'll have a 20 kV glove for that first voltage, 7,200. And then they'll have a 40 kV glove for the 19,900. So that really means, in all essence, you've got 4 sets of rubber gloves, 2 off being tested, 2 with you while you're doing your work. So you got to keep up with 2 sets while they're there. When you get your rubber gloves and you send them off and they come back, they should be stamped, tested with the date.
Right.
Always check that. Always check that the most recent date of return is on your rubber gloves. Sometimes they do get looked over and you'll get the old set of rubber gloves back that never got tested.
Yep.
Okay. All right. Treat those things like gold, gentlemen. They are, just like Professor V said, your lifeline.
That is.
Okay. Anything else, Professor V or Lennon, you want to add?
Anybody else?
No, sir, I'm good.
Okay. Well, let's go ahead and get a little refresher. We're going to have a quiz today. Got quiz today, exam tomorrow. And like I said before, exam is comprehensive. So there's nothing new on the exam that you haven't done before. It's just a compilation of all that you've done in math. So let's refresh. I'm going to bring up a whiteboard here. And we'll talk about ratios a little bit. You should see a whiteboard.
Yep, it's coming up.
Is it there yet?
Yep, just came in.
Okay. So let's throw a couple transformer situations out there, different voltages and whatnot, and we'll work out some ratios and get the ratios back down to where we were before. I'm going to draw my little transformer in, maybe. Here we go.
There we go. Beautiful,
Isn't it sweet?
isn't it?
Everybody have a good weekend?
No?
Oh yeah.
Good. Good day off, fishing, hunting.
Sir.
Went to the
Mhm.
beach.
Okay, so I've got a transformer in my primary voltage. Why does that do that? Primary voltage is 7,200. And the output voltage, remember, I'm going to get 120 out of this leg. That's neutral going to ground. Get 120 out of this leg. When we're doing computations on transformers, we always use the total voltage. So 120 is 240. That's my secondary voltage. And what's the ratio of this transformer? What do I need to do? Boy, that was a long weekend.
Divide 7,200 by 240.
Excellent. 240. and take 7,200 and divide it by 240, which equals what?
30.
I'm pulling it up. 30, 1 to 30.
30, right, 30 to 1. Okay, a good simple check right here to make sure everything is right is take 30 times 240. That should give me 7,200. 30, 240, 7,200. All right, that's a ratio figure for that voltage right there. And you know, Professor B, I might use one of your voltages. Let's try another one. 19,900. $480 volts. That's my output on secondary. What's the ratio? Get those phones out, burn up those calculators.
4.5,
4.5,
No,
1.45.
1.45.
no,
41.5.
Yeah, you're just cutting in and out. I was waiting for that answer. So 41.5, correct?
4.5.
4.5. Okay, sorry about that. 4.5 to 1. That's the ratio of that transformer. Professor V, give me a voltage of yours.
13,200.
13,200. One, two, three. I'll go 240 down here. What's the ratio of this transformer?
55 to 1.
55.
55. Okay, so simple explanation here. We're doing, every time we're doing a ratio, we're doing the primary voltage divided by the secondary voltage. Primary voltage divided by the secondary voltage. Primary voltage divided by the secondary voltage. All right, and what'd you say that 1 to what?
55.
55.
Okay, that's the ratio portion of what you need to do to get the number of, and that is a question on the test. Of course, you're going to have maybe a different voltage out there. But if I ask you what the ratio question is, that's what you're going to be looking for. Was there a question?
Yeah, is it 1 over 41.45 or is it 41.45 over 1?
I just draw it this way. If you want to put it like that. Okay, it depends on which direction you're talking.
Yeah, because that's where I got tripped up the other day.
Okay, and it's me and my process, and I'll show you here in just a moment what we're talking about as far as doing the math. Okay,
Right.
so let me clear this screen up, and now we're going to add an amperage value, and we'll use let's see, I draw this one a little bit bigger. 7,200, 240. 1, 2, 3, primary, secondary. So our figure from this one before was what? What was our ratio?
1 to 30.
1:30. Now the reason why I do this here, Mr. Embry, is if I put 1 amp through my primary side, 1 amp through here, how many amps will there be on the secondary side?
30.
There you go. All right, that's why I draw it in this fashion. It just helps me visualize where things are at.
Okay.
Okay. Obviously, if I go in reverse and realize the math that you did down here, if your ratio is 1 to 30, you at 1 times 30 equals 30. Okay. 30 divided by 30, if I want to figure this top number equals what?
1.
There you go. That's why I draw it in this fashion when I go that direction.
Okay.
All right. It just helps my brain out as far as
For sure.
seeing how things go. So let's throw some different numbers to it. 19,900. We use that same number, 480. I like drawing the transformer in. It just helps me visualize things a little bit better. 1, 2, 3. I think that was 1 to 41.45. Is that right?
Yes.
41.45, yeah.
Okay, let's change up the numbers as far as amperages are concerned. I've got 7 amps on my primary side. How many do I have on my secondary side? First, tell me what the math is. What computation am I going to do here?
I equals,
No. We're just figuring ratios. I'm not asked for power. I've not asked for resistance or anything like that. I've got an amperage value and I'm asking for another amperage value. So Ohm's law does not work in this. When I'm going down and I'm looking for the bottom number, 7 times 41.45 equals what?
okay.
What's that, math?
290.15.
290.
290.15.
Okay, you're cutting out there.
290.15.
Gotcha. All right. That's my answer. That's the answer I'm looking for. You'll notice in this question, I do have 2 voltages here, but I'm giving you an amperage and I'm asking for an amperage again. So Ohm's law does not factor into this at all. If I'm looking for I'm going to go a little off track here. If I'm looking for power, I'm going to have to give you a voltage and an amperage. This is not the case here. I'm just asking for ratio. All right, so another solution here, or another way to think about this, and then we're going to do another one here in just a moment. And then it's time for me to get my breakfast of champions, Diet Dr. Pepper. V, what was yours? 13,000 what?
200.
200. 240. One, two, three. That's an awfully flat transformer. What was our ratio?
1/55.
Okay. 155. Now we're going to go the opposite direction in our calculation. I'm down here at the service side, and I measure 262 amps. All right, that's my amp value on the bottom. Now I want an amp value at the top. What's the math involved now?
Divide it.
Right, if I multiply going down, I divide going up in my calculation. I'm looking for the up number. 262 divided by 55.
$4.72.
4.72. Okay. All right. We essentially did right there also, just by getting one reading down here. We also know, and we'll talk about this in a little bit when we do our math part, what the fuse is doing. So if we have 4.72 amps going on the primary side, we know what the fuse is going through the fuse itself, because remember, our transformers are fused. Any questions there? I think this does disrupt some students, and we've seen it before. And Professor V can attest to this too, is if I give you a question, if there's a question out there, 1, 2, 3, 480V, 7200V, and I give you an amperage, and I ask for the other amperage down here, that is a ratio only question. No Ohm's law. Okay. Gave you an amperage, asked for an amperage due to the ratio, 7200 to 480. So no Ohm's law is involved. Now that's not to say that we might have some questions on the test there that you have to figure the amperage first and then use Ohm's law. What time are we holding here?
8:32.
Okay. And then you have to use Ohm's law because that is going to happen on the test. Once I have, and it's sitting right here. If I've got 10, let's do this one real quick and we'll take a break. If I've got 10 amps, first, what's the ratio? 7,200 divided by 480.
15 to 1.
Excuse me?
I think it's 15 to 1.
15 times 480 is 7,200?
15 times 480, yeah.
Okay. So 15 to 1, 10 times 15 is what?
150.
150. All right. So that's the first part of the question. Now, if I ask you, if I give you, you've got two values now, both on the bottom and the top. If the test question continues to say, how many watts? Are being used? Now Ohm's law factors in. What do you have supplied? I've got a voltage and an amperage. Actually, twice. P equals E, which is voltage, times I. What's 480 times 150?
72,000.
I heard part of that.
72,000.
72,000. Okay. What? Check this out. What's 10 times 7,200?
72,000.
How about that? We could have figured it from the top number two. They both work. What size transformer should be here? It goes 25, 50, 75.
75 kVA.
75.
There you go. So you see how everything kind of factors in. You just got to know the timing of when to use what. My question started out with, I need the ratio, 7,200 to 480. You got it. I gave you an amperage. You got that. Then I asked you for a wattage. Then you got that. All right, let's take, what do you think, Professor V? It's Monday morning.
50 or
8:50?
8:50.
8:50, that sounds like a plan. Everybody get you some coffee and Wheaties, whatever you do in the morning. We'll be back at 8:50. Okay. So. Professor V, I'm just going to jump right into the quiz.
Okay.
And we're actually going to do a review of the questions.
Okay.
Okay, so. You know, and I like to bounce back to what Embry said before about, well, why do we need to know so much about this particular thing in math, at least? To be honest with you, this is going to factor into ELW 112, 111. It's good to know this information as far as what you're going to need to compute and do transformer sizes and whatnot. And also, especially when you get called out on a trouble call and you're working with somebody, first, I want you to be impressive and know your stuff. And I'll have to admit, I know Professor V is really good at this, especially in his situation when he worked at Georgetown, because he was on his own a good bit, is you guys got to be somewhat of an investigator.
Mm-hmm.
You got to deduce some things and factor some things in there to make the best decision, not only for yourself, the customer, but for your company as a whole. If you oversize something, you're wasting money. If you undersize something or do something wrong, you're gonna have to go back to it. And again, that's a waste of money, and then your customers are not happy. So that's why we learn these things in the way we do. I'll give you an example in this math portion right here. So I've got my screen up. Everybody see my share screen?
Yep.
Okay. And we'll throw a transformer up here, and we'll just do the simplistic one, 7,200, 240. And you guys, when you work for organizations, let me throw this out right here. We probably have discussed this before. I know I discussed it this morning. How many different distribution voltages do I have at Santee Cooper?
Three?
Just, well, two distribution. All right. My phase to ground voltage for one is 7,200, and my phase to ground voltage on the other voltage is 19,900. Now, let's get a little description here. What do I mean by phase to ground? If you remember by our training yard, and we'll just use one of our primary phases here, and ground is actually the neutral, because what do we do with our neutral? We ground it. So that's going to be 7,200 on my primary phase, then neutral is grounded. That's a voltage measurement between there and there. Okay, we'll talk more about phase to phase later on in our course, but as far as we're concerned right now when we're talking, we've only got to know, at least for my organization, two different voltages, 19,900 phase to ground and 7,200 phase to ground. Okay, Professor V, when you worked at Duke, you said you had three?
Right, correct.
Yeah, so really in the long run, you're gonna start working for an organization here, and you're gonna, first, where can I get this information? 7,200 and 240 without even making a measurement. Where can I find that information on the transformer?
On the
On the
nameplate.
tag.
Yeah, right, on the nameplate. So that's the great indicator right there, and lets you know what's going on as far as the voltages are concerned with this transformer. Now, you're just going to go 1 to 30 very, a large amount of times. That's our main distribution voltage right there. You're going to know that from here on out. 7,200, 240 to a home is a 1 to 30 ratio. It's just going to come to your mind automatically. Okay, it's just going to be like that all the time. What you need to look out for is, well, what if I change my voltage to 480? Say I need to use this on a pump or something. I need a higher voltage. Then you're going to have to compute that. Okay, so going back here, let me start with a fresh screen. All right, let's do one right here. 2, 3, 4, 5. Bam, 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 bam. All right, 7,200, 240. Okay. And you're going to the transformer and you're getting a complaint. Some people say it's humming too loud, or the lights are going dim and bright. And you take some measurements off the transformer, an amperage measurement, and you've got 260 amps on the secondary side. All right. Now that's all I'm giving you. Do you need to figure ratio here? I want to know, is this transformer big enough, or is it too big for the situation that I have? Am I asking for ratio here? Yes or no? No, you're not. Okay. I'm asking for P. That's this number right here, power. I'm giving you I, and I'm giving you E. Here's where I'm question mark is. P equals E times I. So let's go ahead and throw that math in. 260 times 240.
$62,400.
62,000. Sorry about that. No, I'm not going to erase it. 62,400. Okay. Here's where you guys have to put your minds to work a little bit. First, what size transformer should be at this location?
65 kVA.
There's no such thing. I'll put them over to the side here. No problem. You guys will learn.
Uh,
25, 50,
75.
75. Okay. Now 75 is going to be a little bit of overkill, right?
Yes, sir.
What have we not factored in here? We missed something. A 50 kVA will actually do what?
Is it 150%?
Right, which is 75 kVA.
Yes, sir.
There you go. It'll do 150%. Okay.
Yeah.
All right. So that's one factor. Would I go with a 75 kVA? Listen to this closely. If the temperature was 70 degrees outside, it was a calm day. Should I put a 75 there?
No.
No, no, I'd leave it as is. Okay. All right, I'm at 150% and it's 112 degrees, hot and sunny. Should I put a 75 there?
Yeah.
I probably would. Because, you know, it's starting to get up in the peak areas right there. So I'd probably go with, yeah, I probably need to up to a 75 kVA just because of the conditions. All right, that's where you got to use your investigative minds. That's really why we're doing all this. So you can make a good decision right there in that scenario. Okay. So let me go jump back here to the questions. Professor V, just keep an eye on my time for me.
Gotcha.
Okay. Wow, it takes a long time to load. The transformer primary voltage is 19,900. And the secondary voltage is 277. That's one we haven't seen in a while. What's the ratio? What do I need to do?
Divide 19,900 divided by 277.
All right, give it up.
71.84.
All right, so it's 171.84. Simple solution right there. That's all I'm asking for in the question. Okay. I might mix these up a little bit, Professor B.
Mm-hmm.
All right, let me clear this one. All right, transformer primary voltage is 19,900. Secondary voltage is 480. Find the ratio. Think
1
that
over 41.5.
1 to 41.5, correct?
41.45.
45, thank you. All right, the question continues on, and this is why I like to write them out. How many amps will be on the secondary side? So I'm going to throw a question mark down here. I don't know. If there are 3 amps on the primary side. So if I have 3 amps on the primary side, how many amps will I have on the secondary side? We're going down on our, well, I almost said it. We're going down in our calculation. What do I need to do?
Multiply.
Multiply.
You get 124.35.
There you go. Question answered. All right. A service, and this is a service that goes to your house, has a voltage of 240 volts. And the current is 62 amps. What size transformer is needed for this service? All right, first question here. Do I need to determine a ratio?
No.
Yes.
I don't even have anything to determine a ratio with. I'm giving
Oh,
you an
yeah.
amperage value and a voltage value, and I'm asking for a power value. Okay, so what's the math? P equals E times I. What size transformer should be in place?
15 kVA.
Or what was your math? 6,200, I mean, 62 times 240.
Yeah, I got 14,000 something.
14,000 something.
Let me look again. I got 14,880.
All right, that's perfectly almost spot on the 15 kVA transformer. So that is correct, 15 kVA. While you bring that up, guys, Professor V, you did hand out the paper charts, right?
I did.
Right, you guys got to reference the paper charts as far as your fuse sizes and transformer kVA sizes, or they're still in the D2L ELW 110 homepage. That chart is in there if you want to print it out or have it in a Word document off to the side. All right, do not put 14,000 something as the answer. You're going to have to select the correct kVA and correct fuse size when you do these questions. All right. Oh, this looks pretty, this is different. Let's go the opposite direction on here. Primary voltage is 7,200. And the transformer is a 50 kVA. What fuse size will this transformer need? Do I need ratio?
Yeah.
Okay, I'm not using a voltage over voltage here. I'm using a wattage and voltage. So I really can't compute a ratio at all anyway. All right. I am though asking for I. I'm looking for I. And I'm giving you a V, which in Ohm's law is an E, and a wattage. So what's the math in Ohm's law that I need to use here?
I equals E over A. P over E, sorry.
Right. Refer to your Ohm's law chart. Go ahead and run the math. $50,000 divided by 7,200.
6.94.
6.94. All right. What's the closest fuse size as far as your charts are concerned to 6.94? They go 3, 5, 7, 10, 15.
7.
There you go, on and on and on. Remember, you guys are going to have to refer to those charts on your own. 7 amp fuse. There's your answer. Okay. Good. If at any time you get an equation here, a question that's kind of stumbling you, let me know. Let's clear this screen. Primary voltage is 7,200. Secondary voltage is 240. Primary amps are 10. How many amps are on the secondary side? Aha. Do I need to figure ratio here?
Yeah.
Yep, sure do. 1, 7,200 divided by 40, 30. We're going down in our calculation.
300 amps.
300, there you go. Perfect. Like I said, chat with us. You don't want to raise your hand or anything like that. Let us know if you've got any questions while we're going through this process. Let's see. This is a simple one. How much in kVA will a 50 kVA do in overload? So it's 50 times what?
1.5.
1.5. You converted 150% to 1.5, and that equals what?
75,000.
75. 50 times 1.5 is 75. All right. I'm going to say that question again because you said 75,000 kVA. That's a ton of kVA. That's 7 million something. Here's the question. Read it closely. How much in kVA will a 50 kVA transformer do in short-term overload? Here's my 50 kVA. It'll go to 1.5%. That translates to 75 kVA, not 75,000 kVA.
Gotcha.
Okay. Perfect. All right. Uh-oh. I remember this from days ago. Let's see. A 37.5 kVA has an impedance of 2.6%. What is the true kVA, not wattage, true kVA of this transformer? What's the math? I'm going to take 37,000 and convert that, 37.5 and convert that to 37,000 times 500 times what? Convert your percentage.
0.026.
0.026, and that equals what?
0216.
0.216?
975.
975. Okay. Now it's an impedance, so I need to take it away from my original kVA of the transformer. 37,500 minus 975.
$36,525.
36,525. Now I'm going to read you the first part of the question. A 37.5 kVA transformer has an impedance of 2.6. What is the true, here's the thing, kVA of this transformer? I need to convert this to kVA.
.5
There
kVA.
you go. Yeah, just when I say K, it means kilo, 1,000. 1, 10, 100, 1,000. 36.525 kVA. Bam. Okay, any questions there? A little bit lengthy on that one, had to do a little bit more as usual. Hearing none. Okay. 13. All right. The secondary voltage is 240. And the amps are 212. What size transformer is needed? Well, we've done this before. We just haven't done it with these voltages. Obviously, I don't need ratio here. I don't have two different voltages. But I am
240.
looking for P. kVA is power. So what's the math? P
240
equals
minus 12.
E times I. 240 times 212.
Yes.
Say again,
Yeah, 240 times 212.
which is?
50,880.
All right, well, that's going to be close to one that we're familiar with. And what is that? I'm looking for kVA.
The kVA transformer.
50 kVA transformer, right? That 880 is nothing. 50 kVA is what I need.
Yeah.
Question? All right, hearing none. I heard something.
Yeah.
What's up, Nigel?
Sorry, sir.
Okay. Oh, he must be talking to somebody in the house. All right. So, all right, remember we had talked before, if our transformer will do 150% in overload, will our fuse do the same? Yes or no?
Yes.
Yes, it's got to be able to carry the amperage for the transformer. So I'm going to give you a 65 amp fuse. What will that do in overload? If a transformer will do 150%, then what's 150% of 65?
97.5.
97.5. Now there's a couple different ways to do the math, and I think yours is probably whoever answered that times 1.5 in your calculator. 97.5. Can I take 65 and cut it in half and add it? What's half of 65? 32.5. 97.5. There's a couple ways to get around it and do it, but typically this is the most common. Convert 150% to decimal, which means it's 1.5, and multiply it by 65. Okay. So you're all drawings. Fix that right there. That last question, Professor V.
Yeah.
This is a true or false question. We'll have a little discussion here and we'll have a little teaching on it. I'll ask, I'll throw the question out there to anybody anyway. As far as an electrical system is concerned, your electric utility, what is the most, what time of year is the hardest on the system? I mean, is drawing the most amount of current and is hardest on the system, summer or winter? Peak summer or peak winter?
I think peak summer.
All right, anybody else?
Probably peak winter, I would say.
That's one summer, one winter.
Yeah.
I couldn't hear that.
Winter.
Winter, so I'm gonna put SW. So winter, 2-1.
Summer.
Summer,
Summer.
summer,
Winter.
winter,
Winter.
winter,
Summer.
summer. That's about evened up, isn't it?
Yeah.
Okay. Here's a good way to deduce it right here. And it's got a lot to do with really what residential customers do in the summer, or residential or business customers do in the summer or do in the winter as far as their environment is concerned. This is really what they call it at organizations and companies, is what they call degree heating or cooling days. So let's take some examples right here. Let's see who's on the top right here. Austin Langston.
Yes, sir.
What's your thermostat set at?
About 70.
All right. Dang, man. Icebox. It's 70 degrees. Okay. Now in the summertime, let's just do a close to peak here. in the summertime, let's say it reaches 100 degrees and you got it at 70. How much does your unit have to make up? That's 100 minus 70,
30 degrees.
30 degrees. Okay. So it's got to make up 30 degrees. That's how much work it has to do to keep your thermostat at 70. All right, it's 70 still. Now, what do you set it at the winter? Or just leave it?
Not really. Let me know, honestly.
You want to just leave it?
Yeah, we can just leave it.
Okay, it's 70 degrees. It's 22 outside. How much is it making up?
48 degrees.
There you go. So, guys, which condition here is most severe on a utility?
Winter.
Winter. All right. Winter, as far as load is concerned, when I say load, current flow to customers is more severe in winter. Now, this is for a full electric utility. Obviously, if you live up north and use gas, it's going to be a little bit different. But if you live on a majority electric supplied home, winter is going to be more severe on your amperage draw to utility. The hidden benefit that goes on here is, as far as your lines and your electrical system that's out there in the world, especially overhead, what's better on your system, heat or cold?
Heat.
All right, I'm going to clear the screen.
I would say heat would probably be better on it.
I'd say probably heat.
All right, so we'll go here. Heat, cold. 1, 2, heat.
Yeah, I'd say heat.
3, heat. We're just going to say, with nobody else wants to answer here, we're going to say the heat is better on our system as far as exposure to the world. Transformers, overhead lines, secondary lines, and everything. Heat is more advantageous than cold. Let me give you a quick attribute here, guys. Any conductor, when it's chilled or cold, has better conductivity. Okay, I'm actually, if I have, and I'm not going to throw true numbers out here. If I've got a conductor that's spanning a distance right here, and its normal capacity is 100 amps, if I take and I get that down to say like 30 degrees and lower, it will probably go to 120, just because I've got it cold. That's an attribute of the molecular structure of wire. So let me go back to the original question. What's more beneficial in my system, heat or cold?
Cold.
Cold, okay? So remember that 48-degree difference we had to make up? It's actually offset somewhat by being in cold temperatures for my system itself. Even the transformers themselves, when they get cold, or they're in a cold environment, will actually do better in kVA when they're chilled down and gotten real cold. So here's my question, and it's the last question of the quiz today. A residential customer has its thermostat set to 70 degrees year-round. Winter temps are an average 35 degrees, and summer temps average 90 degrees. This is true or false? The summer temperatures are harder on the electrical system than they are the winter temps. So let's do the math here. Let me clear this. And this helps you guys becoming good investigators of what's happening on your system. All right, so I've got my thermostat set to 70. Winter temps are an average 35, so we'll go 35. Summer temps average 90, so we'll go 90. So that's summer and that's winter. True or false, the summer temps are harder on the electrical system than are the winter temps. So 70 minus 90 equals 20. 70 minus 35 equals 35. True or false? I'm telling you that the summer temps are harder. That's completely false. I have to make up 35 degrees here, where I only have to make up 20 here.
So it's not, it's not something you have to account for when you're out in the field.
It is, and we discussed that before. Here, I'll show you right here. Let me clear the screen, and we'll just use this as an example. I like using a 50 kVA because it's a good round number. And this is why we're doing this in the essence. I've got a 50 kVA. And through my amperage, now we know that P equals E times I. So I'm going to do 240 volts, and I've taken an amperage reading of 460 amps. So figure P for me right here.
$110,400.
Wow. I probably shouldn't have gone that high. First, will the transformer even be able to touch this?
No.
No, it's not. All right, listen up. It's in the coldest day of winter. Should I change this transformer out?
Yeah.
Yes.
Absolutely. And this is probably why it's being driven up so high. The 50 during a calm day is not going to be 460 amps. It's going to be about half that. So it's 70 degrees outside. You got your thermostat set to 70. That's why this thing has been surviving so long out there in the world. All right, you hit a severe cold snap, 10 degrees outside. This thing gets driven up to 110,400. It will not meet the overload situation, which is 50 times 1.5. All right, 150%. That only takes it to 75. It's still over that. It's 110 kVA. By your readings right here, it's time to change the transformer out to what? Careful.
Oh, 75.
Who said 75?
That's what I was getting ready to say too.
Okay, why? Why would you say 75 and not go to 100?
Because it can go, because a 75 can go to 150%, would put it at 112,500.
Excellent. Okay, you probably just saved right around $3,000, $4,000. You're putting a transformer there that will do what?
150%.
Right, which is what?
It's 112,500.
112.5. Right, you have deduced, this is severe for where I live. It's in the dead of winter. Okay, this is going to be the worst it ever gets. So I'll go ahead and put a 75 there, not 100, because it will go to 112.5 kVA. That's where the investigative part and the brain work goes into your deducing on that trouble call. All right, you turn right back around and the guy, your boss man or an engineer says, well, why didn't you go ahead and put 100 there? Hey man, it was freezing cold, ice. 75 will do 112.5 if it needs to for a short-term period. I'm just getting the best bang out of the buck. That was a great deduction right there. I was expecting a lot of people to go to the 100. 75 will work here year-round.
All right, who is that? Al.
That's Al.
Sam.
That's Al. All right, any questions? Well, we're moving right along, Professor Vic.
That's it.
There is a photo here that I do want to show you. Let me clear the screen off. Stop this share. All right. Just to give you a little insight into what we're getting here into the future and why we're learning these things in math now. So let me see if I can find it here real quick. Nope. Here we go. Ah, perfect. Tab. All right. I'm going to share another screen here. I think Lennon had brought this up previously. Let me know when you got that share.
Yes, sir.
Okay. All right. Anybody got any idea what I'm showing you here? Yes.
Like
No?
a giant transformer.
Yeah, when you say giant, you are correct. And I can tell you one thing, you're looking at 500 kV or better coming out of that transformer. And I'll get my mouse over there.
That's a huge transformer. Right
Yeah,
there.
over on this side. I would say that standing here, a man's height is going to be right about to here. Okay. So this thing's huge. One is the voltage coming out of it. Now I'm going to talk about it here in just a moment. And you'll see just barely, those are two conductors coming off the bushing right there. Well, you see the size of them. This is this gentleman, huh?
Is that coming out of a generation station?
It is. Okay. So this is what they call a step up transformer. We learned before that if we hooked up a generator to a normal transformer on the 240 side, we get 7,200 volts out the top. Well, that's what they're doing here at a generating station. What I really want to discuss here is, this is the output. This is my high voltage out. This is my low voltage in. Do you see the size and diameter of these pipes that are coming into the transformer?
Yeah.
Yeah. All right. So really one thing I've got to use here is a very, very large conductor. And you'll notice this gauge that's right here at the bottom. These are usually encased in liquid nitrogen. Now, what's the attribute of liquid nitrogen?
It's very cool.
Severely cold. I mean, they're freezing cold. So they're actually super cooling the conductor from the generating. Now it's insulated into this pipe at a low voltage level into the transformer, and then it goes out, and you see the size of the conductors here at the top, relatively small. All right, maybe 1.5 inches in diameter, where these are, yeah, where these are feet in diameter conductors coming down into the transformer. So I just want to show you that attribute there. The larger the conductor and the colder I get it, the better conductivity it has. You also notice on the transformer over to the side here, you see this big old pipe?
Yeah.
All right, and you see this tank that's on the top. These are radiator fins on the back with fans. So they're blowing fans through oil in these radiators, and this is actually pumping oil through the radiators. So they're also cooling the transformer itself. Cooler you keep it, the better it will conduct. You will actually get a lot more kVA out of this transformer if you just cool the oil in the transformer itself. Okay, let me see if I get one more picture here of something similar. Let's use this one for the cooling processes right here. That is a pretty, wow, that's a pretty cool picture. That's too small. That's the actual wiring process and the coils that you see in a transformer with exposed. That's in being built. Let me go back to this one here. There we go. Open image and new tab. So does anybody see up here at the top? What size transformer is this?
12.
12 megavolt.
There you go. Excellent. 12 MVA. So at my substation, I've got a 12 million volt amperage. So really, how many watts is that in our terms? If KVA, if 50 kVA equals 50,000 watts, what's a 12 MVA?
12 million watts.
12 million watts output on this transformer, okay? So, and that's for Lyman terms. Of course, I told you before, an engineer is going to dispute that because you've not factored out many other things. What do they have on both sides?
Super
So the,
cool.
Yeah, well, right here on these sides, it's not the super cool part. They've got
the radiator.
radiators, right? Radiators and fans. Now, a lot of companies will take these fans and they'll run them by thermostat. So the transformer starts heating up, they'll just come on by thermostat. A good process that Santee Cooper started doing is run these fans all the time. All right, the colder you get it all the time, the better it is. And then this tank up here at the top is meant for oil expansion. You know, oil is going to expand when it's hot and contract when it's cold. So this is just a little bit a reservoir for when that happens.
How come oil was used?
Sir?
How come they use oil?
Mineral oil?
Yeah, why do they use that?
For one thing, you don't want to use anything that's got water in it, okay? The mineral oil is what they call dielectric. It does not conduct electricity, and it just extends the longevity of the coils that are inside the transformer. It is actual mineral oil, all right?
Yeah.
The also included with that is the, what do you call it? Heat dispersion of oil is better than water. All right. Another attribute to that also is oil doesn't expand that much. Water is going to start steaming. Okay. So you don't have much expansion in it. What's the reliability of a transformer?
Very reliable.
Very reliable. 99.9%. You're going to get, and I've seen Professor B, I'm sure has seen this. What's the lifetime on a transformer, Professor B?
Oh my gosh. I'd hate to even say it's probably 50 years maybe.
Yeah, if it's got a good paint job and it's yeah, 50 years. We worked up in Hurricane Sandy up there. We found a transformer. It was from 1908, 1909.
Wow.
Still in service. Still in service. Still pumping out 120, 240. I mean,
Wow.
the thing that makes them the most reliable piece of equipment in the world is 99.9% is no inside here, no moving parts. Okay. Professor V, anything else you'd like to add for today? It feels like we zipped through pretty quick, but
Yep, it's 9:37.
Yeah.
I think it is. You guys got any questions about any of this stuff? How to figure out all these calculations?
I just got one more about the inside of that transformer there. So on the inside, what's happening on the inside? Like what if I know it's filled with oil, but what is it? Is it just the
Coil.
process of the electricity going through the oil and that's what transforms it down or up?
all right. So, I mean, we're gonna, and I don't mind doing this at all. Y'all can hang in there for this. That's the start of ELW 111.
Oh, okay.
Hang in there. Let's get a little. Stay with me. Might as well get a precursor to what's going on.
Yep.
Am I still sharing a screen?
Yep.
I'm going to change it here in a minute, so I'm sharing the audio. You notice I'm typing something in here to be more specific, AC to AC transformer. The utility industry, as far as you're concerned, does not use much DC at all, direct current. We use AC. So I'm going to stop this share and reshare it right back. Now, you would think it would be rather simplistic as far as electricity is concerned. It's pretty, how would you want to say it, Professor V? pretty astonishing.
Okay.
I will include a link to his posts in the description.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at how transformers work. Now this follows on from our series on electrical engineering, so do check out the other videos if you've not done so already. Links are in the video description below. Coming up, we'll be looking at how to create a magnetic field with electricity, why only an alternating current can be used in transformers, how a basic transformer works, then we'll look at step up and step down transformers, and finally we'll finish on three-phase transformers. Now there are two types of electricity, AC and DC, but transformers can only work using AC or alternating.
Okay, so that's something very important to remember. Transformers. Can I convert AC to DC? Now be careful on this one. How do you charge the battery in your car? Can I convert AC to DC?
Yes, sir, of course.
Absolutely. All right. Can I, and you put your phone charger in the wall. That's converting AC to DC. You're charging up a battery. Can I convert DC to DC?
I don't think you can do that.
No conversion possible. I cannot transform that. Can I convert AC to AC?
Yeah.
Obviously. Yeah, we're doing that all the time in our math problems.
Current. Now, if you don't know the difference between these two, then please, first of all, watch the video on electricity basics first. Again, you can find links to these videos and other useful videos in the video description below. When we connect an AC generator to a closed loop of cable, a current will be able to flow through this cable and the direction of the current will alternate backwards and forwards with the rotation of the generator.
Okay, so let's talk a little about this because he went ahead of us. What's inside this generator here where I've got, and this is simplistic, guys. What do I have inside this generator right here?
You have a magnet.
It's a magnet, okay? And a magnet's got a north and south value to it. And a magnet in its own creates a magnetic field. You see that field that's going around the magnet itself. Well, that field is a force. It is energy. Whenever I take those lines of that magnetic field, those lines of force, and I move them, you'll notice they got movement across a coil of wire, current is applied. That is the basics of electricity. As soon as I do that, take a magnetic field and a coil of wire and move that magnet around that coil of wire, those lines of force, current is applied to the conductor. So now I have the flow current.
The alternation means that the current reaches its maximum and minimum point during the cycle, which gives it its...
Now, why does it alternate direction? Watch the magnet. I'm going to go back a little bit here.
of the current will alternate backwards and forwards with the rotation of the generator.
Oh, it moves?
Huh? Because I have a positive pole and I have a negative pole. So one goes one direction, north pole, and one comes the other direction, south pole. It's the property of my magnet. One pushes, one pulls. One pushes, one pulls. Have you ever played with magnets before and tried to put two norths together? What happens? They repel.
Oh, yeah.
They repel. They push each other away. You take the north and south, what they try to do?
They attract.
They try to attract. Well, that's what's happening with the magnetic field when it goes across the coil. I want to push, then I want to attract. I want to push, then I want to attract. Okay? It's got a little bit to do with the direction of the coils and how they're spun, but we're not going to get in that deep right now.
The alternation means that the current reaches its maximum and minimum point during the cycle, which gives it its sine wave pattern when connected to an oscilloscope. Now you can think of this as the tide of the sea as it changes direction and reaches its maximum and minimum point. As the current flows through the cable, it will emit a magnetic field.
So on the conductor itself, let's go back here just a little bit. Not that far, that far. So I've got my generator that's running here. As current flows through this conductor, either direction, it creates a field of magnetism around itself. So there's actually a magnetic field coming off the conductor itself when current flows through it.
Generator. The alternation means that the current reaches its maximum
Back up
and
where we
when
were.
current flows through the cable,
There you go.
it will emit a magnetic field. If we pass DC current through the cable, the magnetic field will remain constant. But if we pass AC current through the cable, then the magnetic field will increase and decrease in strength and changes polarity as the current changes direction.
So my magnetic field is pulsing. Goes one direction, gets real high, goes the other direction, gets real high again. It's pulsing down, up, just like the sine wave that you saw going by. But the big thing to remember here is it's emitting a magnetic field on the conductor itself.
If we place multiple cables together and pass current through them, then the magnetic fields will combine to create a stronger magnetic field.
So the more conductors that I have, the more intense my magnetic field becomes. Same amount of current flowing through it, just more conductors.
If we then wrap the cable into a coil, the magnetic field will become even stronger.
Okay, so if I coil my magnetic field, it's more focused and it's even stronger when I start making coils of wire. While I'm sitting right here, is this starting to look like a transformer? I've got a primary voltage and then a secondary voltage coming out. Starting to look like one. It's starting to build like one.
If we then place a second coil in close proximity to the first coil and then we pass AC alternating current through the first coil, then the magnetic field it creates will induce a current into the second coil.
So there is what's happening right here. So I've got current flowing through here from my generation. It's creating a magnetic field. That magnetic field is cutting, those lines of force are cutting across a secondary coil. So he's already said it. Primary coil, secondary coil. Now I'm going to pause this real quick and show you a little bit of math that's going to go along with it so you guys will learn this. Let me stop this share. All right, share screen, whiteboard, share. Let me clear this up a little bit.
Got it.
All right. This is why we learned math, and this is I told you, everything builds on itself in this course. All right, go over here. All right. So we've got 7,200 volts over here. And by his diagram, that's our primary coil. Okay, 7,200. I'm going to just draw the same thing right here. And this is grounded. Let me draw the transformer in too. Okay, grounded and 7,200 volts in. All right, how many volts are we getting out? 240 V. So I'm going to draw that coil down here. Now it's going to be a little bit different because I need to do a little function here. Okay, there's my coils out. So this is going to go to neutral. This is going to be 120. And this is going to be 120. 120, neutral, 120. Okay. So in essence, what you're seeing in his picture right here, he's creating a magnetic field and they're cutting across the coils of the secondary side. That's what you're seeing. I saw in the video just previously. Guess what? I'm going to ask this question. What's the coil? What's the winding ratio of this transformer? Winding ratio. These things right here. Things that make you go who? What's the voltage ratio on this side?
1 to 30.
1 to 30. What's the winding ratio on this side? Hmm.
1 to 60.
How about 1 to 30? Weird, huh?
Your winding ratio is your voltage ratio.
Exactly. Right. Your voltage ratio determines your winding ratio. So, and that's why we do math, and we learn it in this fashion. So if I've got, and this is my primary side, 1 coil in the loop, how many will I have on my secondary side? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 1 to 30 will convert 7,200 to 240. You guys getting the concept of how this works? Now, if you remember that, and we'll show that picture again, you're not going to see a transformer that's like this, 1 to 30 on the coils. There's going to be tens of thousands of coils to 300s of thousands of coils. It's very small wire coiled up. All right, let me stop this share and we'll head back to the video. And we're going to share the screen again. Oh, let Luke Simmons go.
I'm right here.
I drug you off screen for some reason. All right, back to the video.
And this magnetic force will push and pull on the free electrons, forcing them to move. The key component here is that the magnetic field is changing polarity as well as intensity. This change in intensity and direction of the magnetic field constantly disturbs the free electrons in the secondary coil, and this forces them to move. This movement is known as electromotive force, or EMF. Electromotive force does not occur when we pass DC current through the primary coil, and that's because the magnetic field is constant, so the electrons are not being forced to move. The only time it will cause EMF is very briefly when the primary circuit is opened and closed, or when the voltage is increased or decreased. And that,
which goes right back to what we were talking before. We cannot convert DC to DC. We can convert AC to DC. That is 100% okay.
That's because these actions result in a change to the magnetic field. Therefore, we use alternating current as this change occurs constantly. Now, the problem with this setup is that a lot of the magnetic field from the primary side is being wasted because it's not in range of the secondary coil. So, to fix this, engineers place a core of ferromagnetic material such as iron in a loop between the primary and secondary coils. Now, this loop guides the magnetic field along a path to the secondary coil so that they will share the magnetic field, and this makes the transformer much more efficient. Now, the use of an iron core is not a perfect solution. Some energy will be lost through something known as eddy currents, where the current swirls around the core and this heats up the transformer. And this means that the energy is lost as heat.
Okay, so you heard that part. Eddy currents, all right, anytime you produce heat, and that just goes back to what we were talking about before, anytime that you produce heat in a transformer, which is a normal attribute, it's going to happen when current flows through it. It's going to make your conductivity and your transformer not work as well. So that's why we have radiator fins and fans to help cool that process.
To reduce this, engineers use laminated sheets of iron to form the core, and this greatly reduces the eddy currents. Transformers are manufactured to be step-up or step-down transformers, and these are used to increase or decrease the voltage simply by using a different number of turns within the coil on the secondary side. In a step-up transformer, the voltage is increased in the secondary coil, and this will mean that the current will decrease. But don't worry too much right now about why that occurs. We'll look at this in a later electrical engineering video. To increase the voltage in a step-up transformer, we just need to add more turns to the coil on the secondary side than the primary side. So
take a look at this transformer here. I got one coil that does one revolution. That's a 1 to what?
Down transformer, the voltage is decreased in the secondary coil, which means
1 to 3, and then I've got a 3 to 1. So they're just, you see the difference in the two.
that the current increases. To do this, we just use less turns in the coil on the secondary side compared to the primary side. For example, a power station needs to transport the electricity it has generated over to a city some distance away. The power station will use a step-up transformer to increase the voltage and reduce the current, as this will reduce the losses through the long transmission cables. Then, once it reaches the city, this will need to be reduced to make it safe and usable by buildings and homes, so there will need to be a step-down transformer. The transformers for commercial buildings and power stations are usually in a three-phase configuration. You'll see these placed around your cities and towns.
Okay, we're not going to talk about three-phase. I don't want to get in that deep. Yeah, that's three-phase that carries on beyond. That's in the later part of the course. But does that give you a good idea of how a transformer works? All right, and you'll see also there, I mean, there's a requirement. You need first, you have to have a magnetic field. You have to have conductor, and coils are the best. And you have to have one other component, movement, right? That movement's got to happen back and forth. Where am I getting the movement from in a transformer? Is there a motor in there?
No motor.
No motor. Where am I getting movement from? It's an attribute of AC electricity. Does it go forward and does it go back?
Yeah.
Does my magnetic field go in one direction and then the other?
Yeah.
Yeah, it's more like an invisible movement of a magnetic field. I go out, I go back, I go out. That's how I'm getting movement back and forth. My sine wave goes up, goes down, goes up, goes down. And when that happens, my electricity is going forward, going back, going forward, going back. That's how I'm getting movement. Okay. That's the short and sweet. We'll get more in depth in that later. You guys are going to definitely need to know how transformation works, especially when we start getting to three-phase configurations. All right. Any other questions there? Let me stop. Professor V, anything else you'd like to add?
No, sir, that was really good.
Okay, so it's rolled up to 10 o'clock. Professor V and I will post when the quiz is available. As normal, I'd say we'll probably be available right up to 11:30 today. Then we're going to get a bite for lunch and be available back this afternoon.
Yep.
If you have any questions for us, you can reach us on Zoom. Zoom again tomorrow. And I will let you know now, I will be in Massachusetts Thursday and coming back Friday. So Professor B is going to have the helm those 2 days. And those 2 days will be out at the field.
Are you a mass hole?
Tut? What?
What? Let me stop recording there.